first example is an 875 kilogram compact car speeds up from 22 meters per second to 44 meters per second. What are its initial and final energies, and how much work was done on the car? Okay, so let's do given. So here's the car. Whoops. It's like a little van of some kind, I guess. And its initial velocity is 22.0 meters per second. And then a little while later, it has a final velocity, and it also changed shape somehow. I don't know why. That's right. It's some kind of relativity effect. I don't know. And so there's its final velocity, and we want to know how much work was done on the car to speed it up from here to here. So find the work done on the car. Now, let's solve it. Now, what kind of energy did it have to begin with? I mean, where is the energy of the car? Well, it has mass, and it's moving. So what kind of energy is mass and movement?
Joules.
Huh?
Joules.
Well, those are the units, joules, but what kind of, how is that energy stored? What do we call the way that energy is stored? It's kinetic energy. So we'll call that K initial is 1/2 the mass. Thank you. 1/2 the mass times its initial velocity squared. And so that's going to be 1/2 875 kilograms times 22 meters per second. Let's square that. And when you do that, you should get, when you punch all that into your calculator, you should get 2.12 times 10 to the 5 joules. Now when you do the same thing for the final kinetic energy, 1/2 you just take the final velocity and square that, and when you do that you should get a final energy of 8.47 times 10 to the 5 joules. Okay, so there's oh, I forgot, what are its initial and final energies? I forgot to put that in fine. So K initial and K final. So here's K initial, and here's K final. Now look, obviously the car gained energy. Now where did that energy come from? I mean, this is a car. Where do you get the energy to run your car? You burn gasoline. There was a motor in there, and it burned gasoline and exploded, and that's all thermodynamics. That's all Chapter 12 stuff. And then it transferred that energy through pistons and axles and differentials to the wheels, and through static friction between the road and the car. A force is applied to the car. That force pushed the car to make it go faster. But the work done resulted in a change in kinetic energy, which is K final minus K initial. Now watch this little fancy piece of work, times 10 to the 5 joules. Why did I do it like that? Because I'm too lazy to write times 10 to the 5 joules twice. So I just factored it out. Wow. And so what you get is the work done. When you subtract this from that, you get 6.35. Okay? So this is how much work was done. Now, what I want to do now is show you a bar chart way of looking at energy and where it's stored. Now here's where I'm going to differ from the book. I only use a bar to demonstrate where energy is stored. And I don't like to use a bar to represent work. I like to use an arrow to represent a transfer of energy, because that's what work is. It's a transfer of energy. So here's our kinetic energy container. So think of the car. Here is the initial kinetic energy. And so that represents the 2.12 times 10 to the 5 joules. Now what we're going to do is the engine is going to do work. And that work means we're transferring energy from the gasoline that's contained in gasoline through this complicated series of explosions and mechanical motions and stuff like that. We're going to transfer energy from the, I'll just put gasoline up here, and we're going to transfer energy into there. And what we get is our final kinetic energy, which is obviously much greater. So when we transfer gasoline in this container, it will now be way up here. It's not even drawn to scale. It should be a little higher. So there's my final kinetic energy. So what I did was I started off with this much, and then I transferred energy from the gasoline into here. This was the work done by the engine and the tires and all that to add it into here. So I mean, that's just a way of visualizing what's going on. Okay, and the bar chart thing kind of helps, especially when we get to more complicated problems a little bit later. Okay, let me zoom all the way out. So this is your first example problem. And now you have it all done. Any questions?